In this video, we will learn about the internal rate of return, which is the second of the DMPWs, that is discounted measures of project worth. The first one was NPV, which we have understood. This is the second one, and in this video we will delve deeper into the details of it. Broadly speaking, it gives us a kind of return in rate terms, that is percentage terms of a project, and it is helpful in certain situations. For example, situations where some opportunity cost of capital is given. In a situation where we have some amount and we can either invest it in a project, or we can invest it in the bank, or keep it as a saving in a bank, or invest in any other project. So you see, the alternatives are there. We can either save it and keep it with the bank, or we can invest in any other project instead of the main project. So in this situation, NPV cannot be helpful, because NPV gives us the answers in currency, and it is not comparable with the situations where the returns of the alternatives are in percentage terms. So the comparability is not there when it comes to the percentage returns options, the alternatives, either saving in the bank or investment in any other project. So that's why we have a need for some other tool of DMPW, which is the internal rate of return. We call it internal rate of return because definitely it's a rate of return on annual basis, but it is internal because some people say that it is hidden. We have to work a little hard to find it out. It's not that much clear. We have to do some calculations, some trial and error in order to excavate it. So we have an internal rate of return. Mathematically speaking, it has a certain condition. That condition is that the NPV should turn 0 at that discount rate. So all what we need to know is the discount rate that will make the NPV 0. Here symbolically we have written the same thing, that NPV, if it is equal to 0, this certain discount rate will be the IRR, that is internal rate of return. So the things are little inverted, because in this case we are not finding NPV as we usually did. We are trying to find out the certain discount rate, and for that we have to do a little bit of trial and error. And for that we can exploit a certain relationship between the NPV and discount rate, which is the inverse relationship. As we know that in discount rate, when it increases, the NPV will decrease, because the very formula has both of them in a way which are going to be inversely related with each other. But this is not going to be a straight thing. We have to do some trial and error for it, and we will increase the discount rate, and then the NPV will decline, and we want it to become 0, and that is that discount rate that we can call as IRR. So in search of that, we are going to do this trial and error. There is another thing, because if the first time if we increase the discount rate, if the answer doesn't become positive, negative or 0, then we have to do another trial and error. So we are going to increase the discount rate one by one, that is bit by bit. So what should be the certain level of change? Should we do just random changes? Yes, we can, but the decorum is that it should not be more than 5. It should be either 5 or less than this. This has a certain implication that we will see as we look into the second part of this video, which will be another separate video to explain the reason why this gap is limited to a certain extent, that is 5. So convention is this: it's not a carving in the stone. We can change it, we can reduce it. If we reduce this gap, it will be a good thing. Now we can see all of it in a numerical situation, where we have taken an example from the planning manual, Government of the Punjab, where Lahore Sialkot Motorway is being analyzed. We have seen this example before. We are going to use the same data. In the first column we have years, then capital cost and operation and maintenance costs, then gross costs, which is the sum of the two. and then we have the benefits, and then the net benefits are there, which are definitely the difference of the two. So we get these values. We must not forget that this stream of benefits and costs is spanning over 10 years, as we have used it before. So after this we can do the discounting, for which we have discounting factor, which we have done before multiple times, how to calculate the discounting factor. And you can see that we have calculated it for 12%, because for 12% we have the convention, and we use it whenever it is not given. In this case it is already given. So at 12% we will discount the net benefits, which will become the discounted net benefits, and then this stream will be created after we multiply the net benefits with the discounting factors. Now after this we will take the sum of it, and the sum is this, which is the answer of the NPV at this discount rate, which is positive. And then we can talk about the discounted net benefits. It should be clear that this is the correct value of the final year, and this is the correct value of NPV. This is a small correction that should be done. So after this we can see that the NPV at 12% discount rate is positive. We want it to turn 0, so we have to increase the discount rate from 12% to another higher level. And we already know that 5% difference is suggested. So after 12% we calculate the discount rate at 17, discounting factor at 17%. So the discounting factor is recalculated by using 17%. So you can see there are different values as compared to the values calculated with 12%. So the difference is visible. Therefore we calculate the discounted net benefits again, and this time net benefits are the same, but the discounting factor is now at 17%. So multiplying this term, that is this first discounting factor, with first net benefits, we will get this value. And the same way we can calculate the remaining discounted net benefits that are calculated at 17% discount rate. So when we sum these values to get the NPV, that is the sum of the discounted net benefits, it is positive. It is 21.2715, which definitely has declined substantially, approximately by 50%, because it was 41.2334 and now it is 21.2715. So it's an encouraging sign. However, we have still not reached the destination, and that is 0 NPV. So we should further experiment, and in the next part of the table we are going to do the same. Instead of using 17%, now we are extending it to 23, which means that we have added yet another 5% in it, just to continue the trial and error. And again you will see that the process of calculating the discounting factor is there, and we are calculating the discounting factors at 23% discount rate. So you can see 23 discount percent is the discount rate. Consequently the discounting factor is now this, and then all these values are visible that you can easily calculate. In the first column we have continued the net benefits, because we will need this. We will be multiplying these values with the new discount rate, that is at 23%. So now we will multiply minus 20 with this, and I'll get this. So this is the first discounted net benefit at 23% of discount rate. And then we can do this thing again and again. That is till 10 years. This is the discounting factor of the final year, 23%, and discounting factor is getting multiplied with the discount net benefits of the final year, and I will get this as the product of the two. So all these values, they are the discounted net benefits that I can easily add. and when I add them I will get this certain value, which is 6.0799. Now from 41 approximately to 21, it has now become 6 approximately. So now we are optimistic that if we do this trial and error one more time, that is if we convert the discount rate 28 from 23, that is add 5% in it, then we will have a negative NPV. So we do this experimentation again. 28% is that discount rate on which we are calculating the discounting factor. The first value will be this, you can verify, and then the second value of the discounting factor, and then the third value, and so on at 28% discount rate. Again I will multiply this with the net benefit of that year, and I will get the discounted net benefit at 28%. And in the same way I can calculate the discounted net benefits at 28%, and I will get 10 values as the number of years is 10, and this is at 28%. And now when I sum them, the sum of the discounted net benefit, it is negative. So I have finally found a point where I can build the formula and try to get to 0 NPV, because I know this is the positive NPV and this is the negative one. So in the middle there will be a discount rate at which the NPV will be 0. So for that I have to build some logic, and then a formula will be used. I should note the values with certain names. That is, I can see that 23 is that discount rate at which the last positive NPV occurred, and 28% is the discount rate at which the first negative NPV occurred. So 23 is a lower value as compared to 28, so I call it lower discount rate. So 28 definitely is higher as compared to 23, so I call it higher discount rate. And then I have these notations IL and IH. They are representing these values. We should also pay attention to the NPVs. NPVs, they are calculated on both of these levels of discount rate. NPV at lower discount rate was 6.0799, and NPV at discount rate higher was minus 1.9826. So it is not the higher value that we are talking about, it is the NPV at lower discount rate, or NPV at higher discount rate. Discount rate will remain the pivot around which we will name these variables, and it is not about the higher value of NPV, because NPV at lower discount rate is higher as compared to NPV at higher discount rate, because you know negative relationship is there. If the discount rate is 23, NPV is higher. If discount rate is 28, NPV is lower. The negative relationship is visible. So we name them as they should be. Now there is a formula that we have. We will come to this blue column, these blue columns later on. What we can do is that we can get the NPV is equal to 0, which is the main purpose to get to IRR, and definitely it should be between the positive and the negative NPVs that we have highlighted, and accordingly there was a lower discount rate and a higher discount rate that we can use to interpolate. Now I'm using this word interpolate because inter means between two and poles mean two extremes. It means that there is one positive value and there is one negative value. So these are two poles between which we are trying to get something for ourselves, and that is the discount rate at which NPV becomes 0. So this is the formula that we will use IRR interpolated. It is interpolated because the actual IRR, the true IRR, is not there. This is an approximation that we are using. So we must remember that this is a kind of approximation that we are using. It's not going to give us a precise answer. We will delve deeper into it in the second part of this topic. So the formula is that we write the lower discount rate and then we add the difference of the higher discount rate and the lower discount rate, and then we multiply this term with the ratio of the NPV at lower discount rate and the sum of the NPV at lower discount rate and absolute value of NPV at higher discount rate. You can see that the absolute signs are used. Why? Because the NPV higher is always going to be a negative value, because between negative and positive values is the zero NPV that we are looking for. So naturally one of the NPVs that is at higher discount rate will be negative. So this is the formula, and easily we can substitute the values and we can get to the answer. Here we have done the same, that we have substituted the values, that is lower discount rate, higher NPV, higher discount rate, and this NPV at higher discount rate, which is actually lower, and NPV at lower discount rate and NPV at lower discount rate, the value of which is actually higher because of the negative relationship of NPV and discount rate. So we can easily solve it, and the answer is this. Now definitely we need to interpret this answer to make some real life meaning of it. So this is the answer, and we can call it the interpolated IRR. Now we need to compare it with the opportunity cost of capital. It is again that thing that we were assuming in the beginning, that the bank is giving you a kind of return, which is the opportunity cost of capital, and definitely this is that value you can get if you do not go for the project. So these are the two things that are being compared for for making a decision if we should invest in the project or we should save in the bank. So opportunity cost of capital is a suitable name because this is the opportunity cost of capital that might be invested in the project. So we can check from the bank that what is the return that they are giving to us on annual basis, and then we can be in a better position. Definitely if the for example, if the opportunity cost of capital is 12%, then it is better to undertake the project because IRR is 26.705, which is higher than 12%. So it means that project on average on yearly basis is giving us a greater return as compared to the opportunity cost of capital in which is available from the bank or any other project. So in this case the project seems to be a desirable project, and we recommend that we should undertake this project instead of investing the amount somewhere else. However, there are other possibilities as well. Not every time the project is desirable, as the IRR can be either equal or less than opportunity cost. Then definitely we will look for the other alternatives, that is we will go for the bank or any other project. And if they are equal, we are indifferent, and in case of being indifferent, we can either go for the project or the alternative. So that will depend upon other factors. The direness of the need of that project can make that project get selected, and if there is no dire need of the project, then we can do either of the options or either of the alternatives. So in this way we can calculate the IRR and we can interpret it. However, it is very much desirable to verify our answer, because this was quite a bit of lengthy calculation, and you can expect that in any other project the trial and error can go to a higher level. For example, if the IRR is about 50 to 60%, you can guess that you will have to take quite a bit of jumps to get to that level. That is, if you start from 12%, and if the IRR is hidden somewhere at 60%, then definitely quite a bit of jumps will be required, 12 and then 17 and then 23 and 28. So trial and error can really get quite tedious and tiresome. In that situation, you can use your understanding of how the value of NPV is changing. If the NPV is very slowly changing and not reaching close to zero, then you can make a big jump. That is, you might go to, for example, 50 straight away, and then see that if you have a negative NPV or not. If you have a negative NPV, then you can come back and see that if at 45% if we have a positive NPV, and if it is so, then we can interpolate between these two levels of discount rate. So it's not a binding that we will get the answer quickly. The answer can be hidden at a broader scale. For that we can make a big jump, but remember, keep the difference at maximum 5%, not more than that, because the more you increase it, there will be a problem that we will discuss in the second part of this video. So we would like to keep the difference by 5%, no matter how long the jump is. We need a positive NPV and we need a negative NPV in order to interpolate, and the difference should be at maximum 5. So this is one thing, but after all of these calculations, we can still be doubtful if our answer is correct, that is, if IRR is correct, and we can do this verification, and this verification is visible in this blue color. We have written IRR here. So for verification, I'm going to use IRR instead of discount rate. Definitely IRR is also a discount rate, but that certain discount rate. And in this example, the IRR was 26.7705 as we just calculated. So here we will calculate the discounting factor at IRR, and the answers will be there of the discounting factor. As you can see, I have calculated all of these values are the discounting factor at IRR, which is 26.7705%. I have kept a high level of precision by choosing 4 decimal places, which is a good thing. So once if we have calculated the discounting factor at IRR, we are going to multiply it with the net benefits, and we will get the discounted net benefits at IRR. So these will be the values which we can sum to get the NPV, and here they are added, all these 10 values. The answer is minus 0.2908. So it is nearly equal to 0. We can say that it is nearly equal to 0, but not precisely equal to 0. This is the NPV at IRR. That's where the problem or limitation of IRR arises, one of it, and it is that when we are trying to use this interpolation formula, it is leading us to an NPV which is very close to 0 but not exactly 0. We will unravel this thing in the next part of this video. However, in this video we have learnt that how we can calculate the IRR, for which we have done quite a bit of interpolation as well as trial and error. And after that, what we did is we verified it, and the verification highlighted that we have an approximate value of the IRR and not the precise value. And for the removal of this issue, or at least recognition of this issue, we will make another video, and that video is the second part of this video. Thank you.